Okay, welcome to our next lecture in KDD on May the 6th, I guess. Today we will continue with the topic of preprocessing data. Last week we started with introducing some different kinds of dirty data and how we can handle them very high level. Today we will start at the last slide we stopped last week, data integration. First things first, are there any questions regarding last week? Okay, doesn't seem like that. Then, before we continue, again, also a little service note. The Wednesday exercise is not taking place today due to illness. Everybody who is in the Wednesday exercise should visit the Thursday or Friday exercises if they didn't visit the Tuesday or Monday exercises. It might happen that people get ill, so that's the case today. So just you are informed. Hopefully Olga also sent a mail out. I didn't receive one, but that's very normal that I didn't receive one. Okay, then let's get to the chapter of data integration. Data integration is very important if we collect data from different sources, and we will do that in most cases. That's something we will also talk about next week during the data warehousing lecture. Because one data source is nice, but if we can combine multiple data sources, we have a lot more data to work with, and therefore our results hopefully get a lot better. By combining data sources together into one coherent store, we of course have to make sure data is consistent. For example, we talked last week about different inconsistencies. For example, genders might be displayed as male and female or M and F in different data stores. That's a case of inconsistency and has to be put into a coherent store. Also, we of course have to integrate schemas. We have to make sure that, for example, IDs that are matching each other are also put onto the same, mapped onto the same scheme. We always have to also integrate metadata, not only the data itself, but also metadata. So, for example, column names, attribute names. There is also a problem that we might have some real-world entities or entities that are the same in both sources, but that are named differently. For example, Bill Clinton or William Clinton, American president, are the same person. But it might also happen with products, for example. It might happen that one product table names a football, WM football of 2026, and the other table names it, I don't know which producer is producing the ball this year, but is naming it Puma XYZ. And they are the same product. That might happen, and we have to make sure that we identify same world entities from multiple data sources. We also might have inconsistencies in a way that we have different representations. We talked about that last week as well. For example, grading schemes around the world are different. We are grading here from 1 to 5, while in India it might be A to F, for example, or America. And we have different scaling systems. Metric systems, British units, imperial units are different as well. We have to match that. One very, very important thing is also not only inconsistencies, but also redundancy. Redundancy is something we want to strictly avoid. We do not want to have the same information multiple times in the same table, because then it might be overweight in the training process, and it gets a lot more complicated, a lot more resource heavy to handle these data. Redundant information might also lead to, for example, real-world entities that are the same not being identified. For example, if we have Bill Clinton and William Clinton in the database, it might be a redundancy that we want to avoid. And, of course, redundancy can also be derivable data. So, for example, if one table consists your birth date and one other table contains your age, both are derivable from each other. Or at least one is derivable from other. Why do we need the age if we have a birth date? We can simply compute that. To detect redundant attributes, we have something called correlation analysis or covariance analysis, which can be used to identify potential subjects for redundancy and which can be handled later on. And it's one of the important steps you should always do if you integrate multiple sources into one data source. Correlation analysis there are multiple different correlation analyses. We will talk about one for nominal data and 1.5, I would say, for numerical data. Let's first start with nominal data. In our example, we have two columns. One column is a person is reading books, yes or no. And another column is a person playing chess, yes or no. And we want to know whether reading books and playing chess is correlating with each other. So there's some kind of redundancy between these two. If they correlate a lot, we can somewhat derive the data from the one column into the other. If we have a table like this, we first have to take an amount of numbers in there. The first thing is to count how many distinct values every column has. Distinct values, in our case, are simply yes and no for both columns. So if we are taking a look at reading books, it has two distinct values, yes and no. Playing chess also has two distinct values, yes and no. Then we have to take a look at the set X of all unique, distinct combinations. So a unique, distinct combination might be yes and yes. Another unique, distinct combination might be yes and no, or no and yes, or no and no. So in this case, we do have 4 distinct combinations. And then we have to take a look at the multiset Y of all tuples. Little side note, every relational database is defined as a multiset. A multiset is a set that can include duplicates. A set is normally not able to include duplicates, while a multiset is able to. So we can have Y and Y 2 times, 3 times, 5 times. So the multiset Y of all tuples is simply Y and Y for first tuple, Y and Y for second tuple, Y and N for the third tuple, and so on. That's the multiset. So we end up with a multiset of 1,500 tuples. These can then be used to compute some numbers. First, we want to know the actual quantity of values in Y. Well, that's pretty easy to compute. Then we have to compute the expected quantity in case of independence. That's more complicated, and we will get to an example that's more obvious to comprehend. The expected quantity is more or less what's the value we would expect a certain combination, so for example y and y, to happen if both attributes are totally independent, so no correlation at all. Both contain totally independent information. And it's simply computed. Oh, let's do that with an example on the next slide. Because of these formulas and these many values, we can also use a contingency table. We also used a contingency table in one of the previous chapters in data. We quickly talked about a contingency table. It's basically the same thing in here. So we are taking a look at every possible value in A, so playing chess, yes and no, and reading books, yes and no. And then we simply add how often each combination is occurring in here. So playing chess and reading books in our example happens 250 times, while doesn't playing chess and reading books is happening 200 times. 50 times for not reading books but playing chess, and 1,000 times for doesn't reading books and doesn't playing chess. Pretty simple. We can of course also add up the values per column and per row, but that's pretty obvious, I guess. The more important part is the expected values. Those are the values in brackets after the real values. So the values we counted are the observed values, and now we want to talk about computing the expected quantity for each of these columns. And that's done by using this formula, which is also printed in here. So let's take a look at the combination of reading books and playing chess. We know that the observed quantity is 250. Now we want to know how many values would we expect if playing chess and reading books would be totally independent. To do that, we first have to take a look at this part, the sum of all values in here. So 300. Because playing chess totally includes 300 different values. By the way, that's also where these sums come in handy, because we already have them in the contingency table if we completed it. For the second part, we do the same thing as we have done for the column in here. Now we do it for the row. So we're taking a look at 450 values. And now we have to divide it through the total number, which is 1,500. And the computation of that, the result of that, is 90. So if reading books and playing chess would be totally independent, we would have 90 persons playing chess and reading books at the same time. We can do that for every other cell in here, and we end up with 210 for 210, we would have computed 300 times 1050 divided through 1500. For reading books and playing chess, we end up at 360, where we would have multiplied 1200 times 450 divided through 1500, and 840 for not playing chess and not reading books. These values are now only an intermediate step. The intermediate step can now be used to apply the so-called chi-squared formula, chi-squared test, to the contingency table. In this contingency table, we simply go through each row and each column, take a look at the observed quantities minus the expected quantities to the power of 2, and divide it through the expected quantity. So in our example, for the first cell, we will take a look at 250 minus 90 to the power of 2 divided through 90, which is this part of the formula. If we now add these things up, we end up at 507.93, which is nice to have. Do you have an idea whether this is indicating correlation or isn't indicating correlation? I don't think so, but maybe someone is in here. But you certainly do not. Two reasons. One is, of course, I don't know whether you have ever heard about chi-squared. Another one is this number is not telling us anything before we know a second number. We first have to define the null hypothesis of a chi-square test. The chi-squared is a test, and a test always has to have a null hypothesis in mathematical terms. In the case of a chi-square test, we define the null hypothesis in a way that we expect independence, so no correlation. And now, by defining it this way, we can use chi-squared to defining a value where correlation is indicated. But which value is needed? To do that, we have to get the critical value from chi-squared distribution. That's done via table, which you can see in a formula collection. In this case, to look it up in this table, we first have to calculate the so-called degrees of freedom. Degrees of freedom are not only important for a chi-square test, they are important for a lot of data science functions, so remember it. Degrees of freedom are simply calculated by taking a look at the number of distinct values in A and the number of distinct values in B. We know that we have two different distinct values in A, and we have two distinct values in B in our case. So in our case, it would be degrees of freedom is 2 minus 1 times 2 minus 1. Well, that can be simplified to 1 times 1, so degrees of freedom is 1. Pretty simple. If you would have 3 distinct values for A and 3 distinct values for B, we would of course end up with degrees of freedom 4. And now the second thing we have to define is the significance level, alpha. The significance level is more or less how likely it is that we are doing a mistake by taking a look at this value. So every test has some degree of possible failure in there. If we define the significance level alpha as, for example, 0.005, it's a pretty low significance level. So we are only tolerating a very low amount of failure, possibility of failure. There are other often used significance levels. If it's less important, we can, for example, also use 0.1, so 10%. Sometimes we are using 5%, sometimes we are using 0.5% in things where we shouldn't have any failures at all. But that's something for a more mathematical lecture, so that's only a teaser. Well, in our example, we already defined degrees of freedom is 1, that's given. We set up the significance level to 0.005. And now we can look it up in a table for the chi-squared values. So we are taking a look at the degrees of freedom, 1, and we are taking a look at the significance level 0.005. And we can see that in a chi-squared critical distribution table, we end up with a value of 879, sorry, not 5. That means that everything above this specific value is likely not independent, but is indicating correlation. And in our case, it's very clear that we are above our threshold. So we reject the null hypothesis H0, which would be independence. And because we can reject independence, we can conclude that there is correlation between the two attributes. Yeah, question. Sorry? That's too quiet for me. How to choose alpha? Okay, how to choose alpha? Well, that's something, as I said, which depends a lot on how important it is that you do not have any false assignments. For example, in a medical study, you would choose a very low alpha because you do not want to make mistakes in a medical test. In something like this, where you're analyzing, playing chess and reading books and simply want to get a feeling for correlation, you can also choose a higher alpha, so 0.1, 0.05. It depends a lot on the subject and how important it is that you do not have any failure. There's no 100% rule of thumb. If you would, for example, write a paper where you do a test for a certain domain, the best thing would be to take a look at other papers in this domain and try to find out which significance level they use for their tests, which should always be part of their paper, so you can see that. And then you get a feeling for how much significance is accepted and how much failure is accepted. If you are in a totally new domain, which is unlikely these days, but might happen, then of course you should take a look at related domains and try to find a level. In the practice, I'm pretty sure that if it's not that important to see, to do not do a failure, people often choose a higher significance level than a lower significance level because it makes it easier to have a successful test, I would say. I don't think that's good to have that. It's better to have a test that is of high significance, but that isn't always the case. Let's say in the exam for KDD, I would give you a significance level if you are to do something like this. Because it's something that isn't given, there's not a 100% correct solution for that. But in the real world, take a look at related domains, take a look at things like that. Okay? Other questions? Okay. I've also linked, and it's a clickable link if you take a look at the documents, these tables. These tables are something that are in every good formula collection, whatever. You find a table like that for chi squared, because you can simply look it up. If you are if again there's a task in the exam where you should do something like that, we would print a table like that into the exam so you can look it up. So there's no need for you to put that into your cheat sheet. No worries about that. If it happens to be part of the exam, we would print the table into the exam, and you do not need to copy that distribution table onto your cheat sheet. Okay. Yeah. Now we talked about nominal data. Of course, there is something for numerical data as well. Because if we would handle numerical data just like nominal data, we would have a big problem. We would have a lot of different distinct values. These distinct values have a meaning to their order, which nominal attributes do not have. So we need another calculation. The calculation which we can use for correlation of numerical values is called the Pearson's product moment correlation coefficient. It's simply a formula where we put in every value for A and B, subtract the mean of the respective column, so column A and column B, and divide the sum through number of total tuples times the standard deviation of A times the standard deviation of B, which can be simplified to this formula: the value of A times the value of B minus the number of distinct values times the mean of both columns divided through n times the standard deviations. If we calculate something like that, we end up with a value above, at, or below 0. If we are above 0, we are positively correlated. The closer we are to 1, the stronger the correlation is. So if we are at 0.001, we have some correlation, but it's not really a strong correlation. It's nearly independent. If we are at 0.9, we have a very strong correlation. If we are at 0, exactly 0, we are independent. That almost never happens. We are almost never exactly at 0, because some kind of correlation, some small correlation might always happen. You have to define the threshold where you skip one column by yourself. And if you are below 0, then you are negatively correlated. What does negatively correlated mean compared to positively correlated? Well, positively correlated means that if the number of A gets up, the number of B also gets up. If you're negatively correlated, it means that if the number of A gets up, the number of B gets down. So they are oppositely correlated. Both things might happen with numerical data. With nominal data, we can't have something like positive or negative correlation. I also talked about we have 1.5 methods for numerical correlation. Because numerical correlation is something we can also identify visually. If we simply plot a scatter plot is something you should know from last week. When we see that we can identify positive correlation, where both values get up at the same time. We can identify negative correlation, where one value gets up, x gets up, while y gets down. That's negative correlation. And we can also identify uncorrelated or no correlation. Of course, these aren't perfect. This wouldn't be a Pearson coefficient of 1, because there's some scatter in these distributions. It's not a perfect line. A perfect line would indicate a Pearson product moment coefficient of 1. This isn't a -1 Pearson product moment coefficient. And this likely isn't a 0 Pearson product moment coefficient. But it tends to be correlated. It tends to be not correlated. And that's something we can also detect visually. Of course, it's better to do a... What is happening? Okay, now it's working again. Of course, it's better to use a real formula to determine correlation. However, scatter plots are something we do as first step to get to know our data set. And if we already detect something like this, it might be necessary to do the full thing and do a Pearson product moment coefficient analysis. Now, a very important thing is the context between correlation and causation. You might already have heard about that a lot of times, but it's that important that I have to repeat it. Let's take a look at these two graphs. If you take a look at these two graphs, it's pretty obvious visually that these two, the blue and the red one, graphs seem to correlate with each other. And in fact, if we compute the Pearson product moment coefficient on that, we end up with 0.8903. So nearly perfect correlation between the two things. Now the question is there any causality between the two? So is one of the two graphs leading to the other graph to do something? A good example for causation, pretty obvious causation, would be if there are less clouds, photovoltaic production would rise. That's causation. Because the sun is shining more on the PV modules and we have more things. If we take a look at what these two graphs show us, we see that the blue graphs are the bachelor degrees in engineering, while the red graph is the electricity generation in Cambodia. I guess these two things are pretty obvious that they aren't causing each other. I don't think that someone doing a bachelor degrees in engineering leads to higher electricity generation in Cambodia, and the other way around. So only because we have a high correlation, it doesn't mean that there's causation between two attributes. That's pretty important to know. There are methods to identify causation strains. These aren't part of KDD because they would take another lecture. They would take a whole module to learn them to you. For you, it's just important that correlation isn't guaranteeing causation. It might be an indication for causation, but it's not a guarantee for causation. Okay, any question about correlation? About the two methods, or 2.5 methods we talked about, chi-squared index, Pearson's product moment coefficient, and of course the visual correlation index. Yeah?
Can we use some alternative terms for the positive correlation and negative correlation, like directly proportional or inversely proportional, something like that?
So the question was whether there are other terms for positive correlation and negative correlation, if I'm correct. Yeah, there are other terms, depending on the domain you are in. With data science, a lot of domains are using data science these days, and a lot of them are using different terms for things like that. For KDD, I would like to stay with positive negative correlation just to not confuse you. You might happen to run across something like that, then you have to look it up. There are often dictionaries that are giving you synonyms between these things, and so you can be 100% sure, but for KDD I would like to stay with positive and negative correlation, just to avoid confusion, because it's only a small part of KDD. If I would introduce every synonym, it wouldn't be a fun lecture. That's something I would like to avoid. Okay? Good. Then let's get to data reduction. Data reduction is the next chapter. I already implied last week, and I think also today, that we want to have as many information in our data as possible, but we want to avoid to have many attributes, many data sets, because of the dimensionality, for example, and also more tuples would lead to far longer computation times as well, or computation efforts, to keep it more general. So we would like to reduce the amount of data we have to process, but keeping the information in these data, smaller data sets, nearly the same or nearly the same. That's data reduction. Which avoids to work on terabytes of data. Maybe we can get down to gigabytes of data. In this lecture, we will talk about 3 major types of data reduction. One is the wavelet transform. One is the PCA, the principal component analysis. And then we will also talk quickly about attribute subset selection or attribute creation. Let's first And we will also talk about numerosity reduction, data compression quickly, but that's for later. And something I'm not sure whether we are getting there today. Dimensionality reduction is the most important thing. So we want to reduce the number of attributes, the number of dimensions we are working with. Because we have this curse of dimensionality, we already talked about, and if we have a lot of dimensions, there's a high likelihood that information in each column is very low, because we have redundancies between these columns. We might have correlation between these attributes. Even if it's not a strong correlation, even if we have a 0.2 correlation in Pearson's terms, then there's some information duplicated in both columns. And if we have a lot of columns, then it becomes less meaningful, less information heavy, the column. Also, we exponentially grow the combinations, the possible combinations with each dimension we are using. So by reducing the amount of attributes, dimensions we are working on, we can avoid or reduce the curse of dimensionality. We can find irrelevant features, attributes, and reduce noise, and we also reduce time and space required for our data mining efforts. One method we can use for that is the wavelet transform. The wavelet transform can be done in multiple ways. We are specifically talking about the discrete wavelet transform. So we are only taking a look at the discrete variant, because for other variants get too complicated. That's something you can also do in other lectures. In the discrete wavelet transform, we are transforming a vector x into a different vector x. X. How it's called? Sorry? X stripe, yeah. Let's call it this way. I'm not sure if that's the correct thing. I'm using X stripe. Of wavelet coefficients with the same length. So we are trying to reduce the number of dimensions we have. The discrete wavelet transform is also very similar to the discrete fast Fourier transform, or discrete fast Fourier transform as well, but is localized more in space than these things. So we are focusing on the discrete wavelet transform. Other lectures might also use FTT, so fast Fourier transform, FFT. But we are doing this one. Basically, in our method, we are taking a look at a vector of data. This vector of data must be an integer, must include integers to the power of 2. So it might include one value. Of course, with one value, we do not need any reduction. We can't do any reduction. Let's say 2, 4, 8, 16, 32, and so on values. If we are not at a power of 2 number of values, then we have to pad the values. And that's something I am often doing in the exam to test whether you remember it correctly. If we are, for example, at 7 values, we have to pad 1 0 at the end. We have to put 1 0 at the end. And then we have two functions, the smoothing function and a difference function. These functions are then applied to the initial vector and splitting it into two different vectors. The smoothed vector and the difference vector. They are half the length. And we can do that until we reach a desired length. Let's do it for an example. Let's start with an already perfect vector. In this case, we have 8 values, so we do not have to apply any padding. Of course. Now we have to apply our 2 functions. One is the average. If we apply the average to the first 2 values, pairs of 2, then we end up at an average of 2. Because the average of 2 and 2 is, of course, 2. And the difference function would be to take a look at the difference between the 2 values, not of the 2 values, but of the first value minus the average, which is 0. We can do the same for the second pair, 0 and 2. In this case, of course, the average is 1. And the difference between 0 minus 1 is minus 1. 3 and 5, that's average 4. Weighted difference is also minus 1 because 3 minus 4 is minus 1. And 4 and 4, 4 and 0. So we end up with an average vector of 2, 1, 4, 4, and a difference vector of 0, minus 1, and 0. We can then apply the same thing to the average vector of the first step. So we can take a look at 2 and 1, compute the average, which is 1.5, and compute the weighted difference, which is 2 minus 1.5, which is 0.5. And we end up with 2 vectors again, the average vector and the difference vector. We can do that again when we end up with a vector with only 1 value in there. If we have done that to completion, to resolution of 1 to be specific, then we can have a table like this one. A table where we have the averages of each step and the detail coefficients of each step with their corresponding resolution. So we are decreasing the resolution every time we are applying the wavelet transform steps. If we are taking a look at the averages and put them into a complete vector, so this is A3, these two are A2, here, 1.5 at 4. Oh, sorry, not 1.5. Sorry, I'm wrong. Here, we have things. The averages is the first average, and then the detail coefficients behind that. Then we have X, and I forgot about the name again. X-stripe was the name. We have X-stripe. X-stripe is basically the same length of original X, so we didn't win anything. However, we didn't win a lot by taking a look at the zeros in here, because we can use zeros to reduce the X stripe length. We can compress X stripe. And it's far more likely that X stripe contains a lot of zeros than it's likely for original, oh sorry, wrong direction, original vector. So by replacing the zeros, or compressing the zeros, we can end up with a resulting vector with less loss than before, because we can use the last average with all the detail coefficients to recompute the original value fairly easily. Yeah. It's a simple calculation because it's a discrete function. For the non-discrete wavelet transform, it's far more complicated, but that's not part of KDD. Let's get to the next function, the PCA. The PCA is also trying to take a look at n dimensions and to find as many, or find new dimensions which include as much information as possible out of the original columns. In best case, we end up with less columns with nearly the same amount of information. The PCA only works for numerical data, but that's the same we had with the discrete wavelet transform. We are using this dataset in here with dimensions 1, 2, and 3. And applying the PCA step by step. The first step of PCA, and it depends a little bit whether that's really counted as a step of PCA or not, depending on the literature. This first step is either a step you're recommended to do or a step which is part of PCA. For the sake of KDD, I define it as part of KDD, of PCA, but you might see that differently in different literature, just as an information. The first step is to get the dimensions to the same information level. So we want that every dimension has the same impact on PCA. And that's something we can do by using standardization. Standardization is a normalization technique we already talked about last week, where we take a look at every value, take a value minus the mean of a dimension, divided through the variance and the standard deviation of this dimension. And by doing that, every column ends up at a standard deviation of 1 in total after the application. So they are considered equally in the upcoming steps of a PCA. If we wouldn't do that step, then we would end up with dimensions with a high range of values dominating our PCA, and that's something we want to avoid. If we calculate the mean and the standard deviation per dimension, we end up with a mean of 13 and 6.5 for dimensions 1, 2, and 2 for dimension 3. And the standard deviation of these values, you can look, try to recalculate these, should be correct, hopefully. And then if we apply the standardization to every data point, we end up with a table like this. So this is simply the standardized table from here. Can also do that. You learn about the methods in Python in the exercise, and you can use that for playing that. Okay. Then the first step of a real PCA, if you want to, is computing a so-called covariance matrix. A covariance matrix is an n times n matrix that contains the covariance between each possible attribute pairing. The covariance is a formula, and I think I skipped it beforehand. Should have been part of this slide. Okay, for some reason I deleted the slide. I'm not sure why. It's a very similar slide to the correlation analysis of Pearson product moment coefficient. Maybe I have to put it back in. For whatever reason, removed it. But it's a formula you can apply, which is pretty similar to the correlation index, Pearson product moment coefficient index, and simply shows how much correlation is between the two dimensions. For the diagonal axis, we are using the variance because, of course, the correlation between two attributes that are exactly the same is 100%. So there it wouldn't make any sense to use the covariance. Basically, we apply the step to identify highly correlated redundant information in the different columns. If we take a look at our case, then we end up with a covariance matrix like this one. I can tell you right now that calculating a covariance matrix is something I wouldn't ask you to do in the exam. It would be too big. You should more or less know the steps of PCA and be able to do them by code, but not by hand in this case, because it's far too complicated, even with simplified values. And you should have done or should do that in the exercise as well, doing that by hand, by code. That's even more true for the next step, the eigenvalues and eigenvectors computation. Because after you have computed the covariance matrix, you're using that matrix to get two different things, the eigenvalues and the eigenvectors of the covariance matrix. And this is solved by, this is done by solving this equation. The covariance matrix times V equals the eigenvalues times the eigenvalues. So V is covariance matrix times eigenvalues equals eigenvectors times eigenvalues. The eigenvectors are the so-called principal components of the data set. To solve this equation by hand, you have to be really, really good because it's a complicated equation. Even in this case, with only 3 dimensions and not that many values, it gets very complicated. So again, something I would never ask you to do in the exam because far too complicated to do that by hand. Of course, in a more mathematical lecture, it might be something you have to do, but not in KDD. In our example, we end up with these eigenvectors and eigenvalues. The eigenvalues are 2.148, 0.815, 0.036, and the corresponding, that's important, corresponding eigenvectors are seen to the right. We are always sorting the eigenvalues and eigenvectors by their significance. That means the higher the eigenvalue is, the more significant the eigenvector is. So we are sorting them from highest eigenvalue to lowest eigenvalue. That's important because the next step is to throw away some eigenvalues and eigenvectors. We are only selecting the top n eigenvectors to create the so-called feature matrix from them. Important, there is no fixed rule how many values you take. So whether you take the top 1 value, the top 2 values, the top 3 values. In this case, it wouldn't make any sense, but the top 4 values, and so on, for a bigger data set. It simply depends on how much information loss you're willing to take. And to estimate how much information you would lose, you can apply a rule of thumb. By taking a look at the eigenvalues you have. And by taking a look at the eigenvalues, you can compute or estimate, it's not a 100% given value, but it's a good estimation. You can take a look at, if I would take, for example, only the best eigenvalue, which is an eigenvalue of 2.148 and so on, and divide it through all the eigenvalues added up. You end up with 0.716. So you end up with approximately 72% of information being contained in this corresponding eigenvector. If you would add the second eigenvector, you can add it up here, you would end up with, I have to estimate, 0.9%, not 90% or 0.9. And therefore you get an estimate of how many information you still contain in the final dataset. In many cases, you would, for example, set the limit to 80% or things like that. Again, depends a lot on your use case. How many information are you willing to give up? And you have to see the trade-off. It's nearly every time the case that this last vector is something you can discard because it contains maybe 2 or 3% of information. No, not even. I would even say 1% of information. So this can be discarded. In our case, we decided 72% of information is enough, so we only select the first eigenvalue and eigenvector, and therefore end up with a feature matrix, which is also a vector in this case, more or less, but would be a real matrix if we would have selected 2, which can be used to continue the calculation. The last step is to use the feature matrix to calculate the new dataset. And that's simply done by using a mathematical calculation. We are using the original dataset and multiply it with a feature matrix. So matrix multiplication. And if you remember, a matrix multiplication of of a 3×4 matrix with a 1×3 matrix ends up with a 1×4 matrix. That's simply done mathematically. And therefore, our result is this one. And this is a new data set containing approximately 72% of the original information. And we avoided a lot of the curse of dimensionality by doing that, because now we have a lot less dimensions to work with. And we removed a lot of the redundancies we had beforehand. Okay. Of course, we can also, if we do not want to have the standardization anymore, turn it around, undo it. However, in most cases, standardization is also good for upcoming methods in data science, not discovering databases. So in most cases, we would leave it at this point, and we wouldn't remove the standardization. Are there any questions regarding PCA? From this calculation, we only selected the first feature matrix, and not the first feature matrix, the first eigenvalue, or eigenvector, and therefore we are able to approximate. Very important, it's only approximation, and we end up at 0.716078885 and so on, which is approximately 72% of information. Yeah. The meaning of a finite transformation is that our dataset, containing 3 dimensions originally, now contains only 1 new dimension. So this would be a new dimension, dimension 1n, 1u. So our new dataset would be simply the one stripe, let's say, with the first value to the second value minus 1.5659, and so on. So we have a new data set, a smaller data set. And that's what we want. We want less dimensions. And that's the data set we are using from now on to apply other data science functions on that. Was that your question, or? Okay. So it's the thing we wanted to have. We wanted to transform the original dataset into a smaller dataset with less attributes, less dimensions. Okay. Other values are, of course, other methods are, of course, also possible. I already talked about the Fourier transformation, but there are far simpler methods as well. For example, we can reduce the dimensionality simply by hand, by taking a look at correlation indexes, correlation values, and simply removing duplicate information. So simply seeing that attribute A and attribute B are correlated 99%, and we simply select one of the attributes to stay. That's attribute subset selection. Sounds fancy, but is simply selecting a subset of attributes to work on. We can, of course, also remove irrelevant attributes, which is also attribute subset selection. If we, for example, know that the student's ID will not give us any information about estimating your GPA at the end, then we can simply remove it from our function. Side note, of course, it's not ethical to compute your GPA by using any prediction methods. That's something you have to do in the exams yourself, but just as an example. Yeah. Okay. Of course, we can do attribute subset selection holistically as well, where we can simply take a look at every possible combination of attributes and try to find the best combination, and also removing attributes step by step, repeatedly eliminating the worst attribute. It can be done. It's very effort intensive to do that, so it's not done that often. But we will talk about something in this direction later in chapter 7, so this is just a small teaser. We can also create new attributes that capture important information more efficiently than the original ones. To be honest with you, we already have done that with Wavelet Transform, and we have done that with the PCA. We have created a new attribute, D1 stripe, from the original 3 attributes, D1, D2, and D3. That's attribute creation. We can do it in other methods as well. For example, we can use domain-specific methods. We can use methods like we had to map the data into a new space. And we can, of course, combine features, for example, using a frequent pattern analysis, which is something we will do in chapter 5. Or data discretization, which is something we will do maybe later today. I'm not that sure about that. Well, that's about dimensionality reduction. We also have numerosity reduction, so reducing the number of tuples we have. Until now, we only reduced the number of dimensions we had. This can be done, for example, by using parametric methods. A parametric method can be applied if we suspect that the values follow a certain function, a certain model. For example, if we have a data set where we have these entries, then it's pretty obvious that we have a pretty simple model lying behind it. It's simply the value d is x is increased by 1 every step, so we have to have id as well times the id. 1 times the id is id, so that's the correct thing. We can simply use a model to find that. This can be done also if we do not have a 100% match, but a rough match to compute the model. Then we only have to assume the model. We also have non-parametric methods, where we, for example, use histograms, clustering, or sampling to reduce the numerosity. Sampling is something we already talked about. We try to sample data to reduce the number of tuples we work with by trying to find a representative sample of a data set. For histogram analysis, and that's also something we talked about in visualization, but we can also talk about in dimensionality reduction. We simply divide the data into buckets and store the aggregate, so the average, most cases. There are some other aggregate functions we can also use for each bucket. There are two different partitioning rules for histogram analysis. We can either have the equal width method, which is we put every value in a certain range with a given width into the same bucket. So every value between 0 and 10 gets into one bucket. Every value between, let's say, between 1 and 10 gets into one bucket. Every value between 11 and 20 gets into one bucket. Every value between 21 and 30 gets into one bucket. So all buckets are the same width. But we can also have equal frequency or equal depth partitioning or histogram analysis, where we try to find bucket sizes which put the same number of values in each bucket. So let's say we have this value, 4, 9. 1, 2, 4, 9. Okay? If we would use, or let's say 10, for sake of simplicity, in equal width distribution, we would likely have one bucket from 1 to 5 and one bucket from 6 to 10. So these three values would end up in the top bucket, and the lower value would end up in the upper bucket. With equal frequency or equal depth partitioning, we would not do that. We would create one bucket from 1 to 3 and one bucket from 4 to 10. These are not equal width, of course. But now we put the first two values in the first bucket and the second two in the second bucket. So we have the same amount of values in each bucket. Okay, two different methods. Most often with histograms we use equal width, but equal frequency is something we also sometimes use. So this would be equal width and this would be equal depth partitioning. If we now have these things defined, we can only store the aggregates of each bucket and therefore reduce our dimensional numerosity. The next function we have to talk about is clustering. Clustering is to store similar data in one cluster, which is something we do with histograms as well. So histograms are basically also putting similar data into one bucket, but in clustering it's more three-dimensional, and then we can, for example, apply hierarchical clustering and therefore reduce the number of values with each hierarchy step we have at hand to contain less and less values. We will do that in chapter 7, clustering, so something for later. And sampling is pretty easy as well. We want to obtain a small sample to represent our whole data set. Of course, we want this sample to be representative. It's not that easy to find a really 100% representative sample. That's something that has to be said. It's not that easy. Because a simple random sampling method, where we simply choose 10 samples from 100 original values, that might have very poor performance in representativeness. While more complicated sampling algorithms are either more labor intensive or need far more information about the dataset than we have at hand. It's also very important to note, if we are working on a database, that sampling isn't really reducing I/O time, because in a database, and that's something you would learn in the database course, not KDD, we have multiple tuples being stored at the same page. Page is a database term, not a book page, but a database page. And if you want a value from that page, you have to take a look at the whole page. And if you sample data from a database, then you might have to look at every page nevertheless. So you wouldn't always improve I/O speed, but you would improve later performance with data science methods. That's simply important because we are in knowledge discovery in databases, so it's important to mention that I/O performance is not improved by that. We have different types of sampling. The simple random sampling is we give every tuple the same probability of being sampled. Of course, in most cases we are only pseudo-random in real sets, but let's assume it's really random. We can still have a not that good random pick. That's something that might happen. And it might happen far more regularly than you think. More sophisticated is sampling without replacement. So we do not have the opportunity of, or not more sophisticated, and we can differentiate between sampling without replacement and sampling with replacement. In one case, once an object is selected, it's removed from a population. In another case, it's not removed from a population. So it can be sampled a second time. In most cases, you would do without replacement because it avoids having a bias on one sample. There are some cases where you would use without replacement. With replacement. For example, if you are doing a medical analysis and you have a rare illness that only happens so and so often, you might need to sample this rare sample twice, thrice, and so on. Which is a rare case, but might happen to apply. Now we get to the more sophisticated method, stratified sampling. In stratified sampling, we try to put the dataset into different partitions which are similar to each other, and then draw samples from each partition. So every partition is represented in the final sampling. Good example would be if I would draw a sample of you in here. I would try to put different genders into partitions. I would try to put different study degree programs into different groups. So I have a data scientist. I have a IT student. I have an IIS student in my sample. I have males and females in my sample. So I can represent you as good as possible. For a medical example, again, it's also important if we have rare illnesses we want to have in our sample, then of course we have to put different illnesses into different groups, partitions, and draw samples from each group. to ensure that they are represented in our final example. And I think the last thing we are talking about today is data compression. Data compression is a huge domain. You know a lot of compression algorithms by using them, at least. Maybe you can't apply them, but you know them if you are creating a zip archive, for example. You are applying a compression algorithm to that. If you are looking at video on YouTube, these YouTube are compressed. If you are working on a database, if it's a more sophisticated database management system, they are compressing data. Because we can often lossless reduce the data amount, or even lossy. YouTube video is lossy compressed, but we don't see it. And we save a lot of data, storage, transport, whatever, RAM, by compressing data. It's a huge domain. In fact, it's my research domain, so I'm working on data compression in databases. I can tell you, even in integer compression, specifically for databases, relational databases, there is a lot of things you can do, and you can fill not only one lecture with that, you can fill several hundred lectures with the contents of that. So simply note that there are compression algorithms to reduce the data. In your case, it might be helpful to apply a compression algorithm to your data before handling them, especially if you have limited storage or you have limited computing I/O or RAM. We can also consider our numerosity and dimensionality reduction functions as some kind of compression, however, a very specialized compression. And I think here we will stop with leaving the last chapter open for next week. That's not a problem, because next week's chapter OLAP is pretty short, so I think we can get through this chapter and the next chapter all in one lecture, which is pretty nice. Are there any questions? I don't think so. Okay, then again, the reminder, the Wednesday exercise isn't taking part today. Please visit any other exercise. And besides that, we see us next week at the same time, at the same place. Have a nice time.